All right, so let's look at example 6 for contradiction. Okay, so it claims the sum of a rational number and an irrational number is irrational, right? That's what it claims. If you wanted to write this in symbolic language, you could say for every x in Q, for every r in reals minus Q, so that's irrational, x plus r is in reals minus Q. So our negation, what we would assume for our contradiction, is that there is some x in the rationals and there is some r in the irrationals, such that x plus r is rational. And that's what the proof would build on, okay? So if you wrote up full proof, you know, it would follow steps we've seen before. So assume for contradiction there exist x in the rationals, there exist r in the irrationals with x plus r rational. All right, then your second line, you know, at this level is just apply your definitions, right? So then there exist, I'm going to call them A, B, C, and D. These are integers with x equal to A over B, x plus r equal to C over D. And what do I need to be careful about with B and D? They're not zero. Okay. Sure, why not? If you don't like that, I could have just put another comma. Or you could say, noting that B is not zero and D is not zero, anything like that. However you want to phrase it. Okay, so here we go. This means, so I'm going to skip some algebra here, but R is going to be C over D minus A over B, right? Because it's C over D minus X, and that's what X is, which is BC minus AD over BD. All right. But BC minus AD is an integer, and BD is in the integers take away 0, right? I'm not dividing by 0 because B is not 0, D is not 0, so their product isn't 0. So why is that a contradiction? Correct. R is supposed to be irrational, and I just showed R is integer over integer. Integer over not 0 integer. So, but that, which means R is an element of the rationals. So then we put our contradiction symbol. I like the lightning bolt. You can use like arrows butting heads or something. I like the lightning bolt. Okay. So R is an element of irrationals, contradiction. So then you go all the way back to what you assumed for contradiction, and its opposite must be true. Its negation must be true. Therefore, no such X and R exist. Meaning the sum of a rational and an irrational number is always irrational. If you ever had a formal logic class, the proof by contradiction kind of falls under the reductio ad absurdum category, which means you reduced it to an absurdity. Here, our absurdity was that R was both irrational and rational at the same time, right? That's absurd. Okay. Okay. Any questions on that one? So we've shown rational plus rational is always rational. We just showed rational plus irrational is always irrational. So that begs a natural question. Is the sum of two irrational numbers irrational? What do you think? Well, let me ask you, what is square root of 2 plus negative square root of 2? 0. So there I have an irrational plus an irrational equal to rational. So the answer is no. Okay. In mathematical language, we'd say the irrational numbers are not closed with respect to addition, whereas the rational numbers are closed with respect to addition. Closed meaning you don't get any new things when you add different rational numbers together. It's still rational numbers. Okay. So I did the spacing a little wrong in the notes. So example 7, you may have to flip to the back of your packet, okay, to write it out, because I don't know, my spacing went wrong in my coding or something. So, all right, well, let's look at example 7. So for every non-zero rational number, there exist two irrational numbers. Well, or they could be the same thing, but there exist irrational numbers such that my rational number is the product of the irrational numbers. Okay. So for every non-zero rational number, I can find two irrational numbers that may be the same thing or may not, that multiply to give me that. So this one, we're actually not going to use contradiction for. I just threw it in here because we're talking about rational and irrational and all that. So we used contradiction already to show square root of 2 is irrational. So we know this is kind of scratch work. Square root of 2 is irrational. I guess we will need a small contradiction in the middle of the proof. So here's what I'm going to do. Let's do our scratch work. X is going to be A over B, right? Because it's rational. So I'm going to let Y equal square root of 2, and I'm going to let Z equal X over square root of 2. What happens when I multiply Y times Z? You get X, okay? So I have my potential irrational numbers. I know square root of 2 is irrational. That's the very first proof by contradiction we did. I technically need to show that that Z is irrational. How do I know there's not some funky rational number out there that when I divide by √2, it magically still comes out rational? We need to show that. But that won't be hard. So that'll be a little part of our proof. So see if I can fit the proof in this margin here if I write small. So proof, we are going to let x be an element, the rational numbers minus 0. Okay. Then there exist a and b integers with x equal to a over b. And this time, neither one is going to be 0, right? Because x himself isn't 0. So even my numerator can't be 0. Do you guys see that? Okay. And neither a or b is 0. Okay. So here's my claim. I'm going to claim that x over square root of 2 is irrational. Have we done a proof that has a claim in the middle yet? Have you guys seen that? Okay, so the way this works, when I have kind of a little side claim I want to use as part of my proof, I separate it out as its own little piece in the proof like this. I'm going to prove that little claim, then I'm going to go back to the full proof, okay? So sometimes we'll even write proof of claim, saying, okay, I'm proving this one little bit. This is my little tangent, my little aside, and then I'm going back. So this is the one part we're going to use contradiction. We're going to assume x over √2 is rational. Well, we know what x is. X is a over b. So, well, then there exist c and d in the integers with d not equal to 0 and x over √2 equal to c over d. I'm trying to write tiny here, sorry. So a over b over √2 equals c over d. Which is equivalent to, let's see, rearrange that. You would have normally done this in Scratch work, right? But we get AD over BC. Well, I know B is not 0. How do I know C isn't 0? What do we know about X? X isn't 0. So X over √2 is still not 0, right? So C isn't 0. Since x over √2 does not equal 0, c does not equal 0. So √2 is rational because I just got it as integer over not 0 integer. And that's our contradiction, okay? Thus, x over √2 is not rational. So sometimes when you have a little claim in the middle, people will put like the unfilled in box, and then when we finish the proof, we'll color the box in to separate the two. So that box is showing I finished the claim proof. okay? All right, so now I want to go back to the original. We'll see how much of this I can squeeze in. We're almost done though. Okay. So actually, let me move over here to give myself space. So I'm going to let y equal √2 and z equal x over √2. Then y and z are irrational. And x equals yz. And that's exactly what we needed to prove, right? The whole thing wanted us to show that I could find two irrational numbers that multiply to give me x. So I just did that. So end of full proof. Okay. As proofs get longer and longer, using that claim method can be helpful to break the proof up, right? Okay. Any questions on that proof? All right. So there is a caution when you're using the method of contradiction you should be careful about. So here it is. Be sure you aren't secretly doing contrapositive. Right. So with contrapositive, that's when we assume not Q and we show not P. So that can be kind of hidden in a proof by contradiction, because with proof by contradiction, we assume P and not Q. So if I assume P and not Q, and I never use the fact of P and show not P and say, oh, I got a contradiction because I have P and not P, you really did a contrapositive proof. And it is cleaner to just show it as a contrapositive proof instead of a contradiction. It's not wrong, it's just kind of looked down upon, right? It's considered kind of, that's just improper way of going about it, okay? Yeah, yeah, it's kind of slang or something. Yeah, it's just not, yeah. So yeah, so be careful your contradiction isn't secretly a contrapositive. Okay. All right. So what's going to happen after this section is you're going to start seeing proofs where it just says, pick a method, any method. So let's kind of look at how you can try to decide what method to use. Okay, that's what I want to do next. So here I have a statement. We have for natural numbers a and b, if a times b is prime, then either a equals 1 or b equals 1. Which one seems to have the easiest approach? So we're going to outline 3 different approaches. Well, we only know 3. So let's do direct first. For the direct approach, what would I assume? A, b is prime. And I would work till I got a equals 1 or b equals 1. Right? Let's think about the contrapositive approach. What would I assume for the contrapositive approach? Perfect. A is not 1 and B is not 1. It's very important that that or became an and. All right. And what would I work to? Yeah. AB is not prime. My other choice would be contradiction. And there you would assume the P part, AB is prime, and not Q. So and A does not equal 1, and B does not equal 1. And then you work till something impossible. All right. Which one of these do you think seems to be the easiest approach? Okay, you like direct? Yeah, so direct isn't bad because ABS prime means it only has two possible factors, right? So A is either 1 or the whole product, or B is either 1 or the whole product. That's a good approach. What about contrapositive? It's a good approach too, right? Because they're natural numbers. So that means if A is not 1, it's bigger than 1, right? If B is not 1, it's bigger than 1. So when I multiply them together, I have two factors, both bigger than 1. It has to be composite. So contrapositive is a good approach. Contradiction here is not a good approach because you would just secretly be doing contrapositive. Okay, so, but it wouldn't be wrong. Any of these three would be okay. So I would say either of these is easiest. And there is an aesthetic to writing proof. So oftentimes finding the cleanest approach, you know, is aesthetically pleasing. Okay, so go ahead, look at the next one. And I'll give you a second to think about it and see what you think would be the best approach for proving this. All right, what do people think? So contrapositive would be the one I'd go to. Because if you let, so contrapositive, because if you let A equal 2K plus 1, then you can plug that in, right, to the A squared minus 2A plus 7 and see what you get, okay? And you will then get that comes out odd. Contradiction would sort of work here, but it ends up, it's kind of secretly being contrapositive because you would do those exact same steps, except you would have this A squared minus 2A plus 7 equals 2L. And so then when you plug in your 2K plus 1, you'll get down and you'll end up with something like 1/2 being an integer. Okay. Yes. Oh, you're right. A is even. Thank you. That's what I get for jumping ahead, huh? Yep, you're right. I need A even. And then you're showing A squared minus 2A plus 7 is odd. And so for contradiction, wait, nope, I was right with that one for contradiction. So with contradiction, you would assume both were even, the original polynomial and A itself are even, and then show that you get a contradiction, and you will get something like 1/2 being an integer or something like that when you manipulate that equation enough. Okay, so either one of those, but contrapositive would be my favorite choice there. Either one works. Direct would be kind of tough. Okay. All right. Any questions on that one? Okay. Page 4. More examples. All right. Whoa, I don't know where Z came from. That should be an A, guys. Yeah, that's called I copy pasted from something or something. Okay. So if I have two integers, then a squared minus 4b minus 3 can never be 0 for integers. If this said a squared minus 4a minus 3 couldn't be 0, I could just use quadratic formula and show the zeros are not integers, right? But a and b are different. So we're going to go about this a different way. So what am I going to assume for contradiction? Yeah, so we're going to say, well, what if a and b are integers, but this does equal 0? What goes wrong? All right, so a squared minus 4b has to equal 3. Well, 4b is definitely even. So what's that mean a squared has to be if I'm going to subtract an even and get 3? Odd. Okay, odd minus even is the only way to get odd if I have an even second, right? I can't do even minus even. So if a squared is odd, what's that mean? A is odd. There you go. You're jumping too far ahead. So a is odd. Now I'm going to do what you said and let a be 2k plus 1. So we get 4k squared plus 4k plus 1 minus 4b minus 3 equals 0. 4k squared plus 4k minus 4b. I'm going to move the constants to the other side. So then I'll get 2 on the other side, right? Plus 1 minus 3 is negative 2. Add 2 to both sides to get the positive 2. This is my scratch work, so I'm just writing out steps I need. Now what can I do? All right, even more than that. I can take out more than a 2. What can I take out? A 4. So specifically, I'm going to divide both sides by 4. 4 isn't 0, so I'm allowed to divide by it. So then I'm going to get k squared plus k minus b equals a half. What do you think?
No, cannot.
It's impossible. K is an integer, b is an integer. K squared plus k minus b, that's still an integer. And it can't equal a half. So there's our contradiction. So then we can go to our proof. So we have our idea. All right, so let a and b be integers and assume for contradiction whatever you're assuming that is the opposite of what you're trying to prove. That's when you put the assume for contradiction. So the thing I'm assuming that's the opposite is a squared minus 4b minus 3 equals 0. All right, here we go. Then a squared minus 4b equals 3. Since 4b is even, this is only possible if a squared and therefore a is odd. Thus, a equals 2k plus 1 for some integer k. Okay, let's say substituting this into our equation. Gives, so what did we have? We got 4k squared, I need to look back here, plus 4k minus 4b, plus 4k minus 4b minus 2 equals 0, which can be simplified to k squared plus k minus b equals 1/2. Let me double check my scratch work, but I think that's what I had. Yep. All right, but k squared plus k minus b, it's an element of the integers, and 1/2 is not an element of the integers. So that's our contradiction. So lightning bolt. And remember, you're allowed to do these 3 dots for therefore. So I'm going to do the triangle dots. Therefore, a squared minus 4b minus 3 does not equal 0. End of proof. All right. Any questions on that one? Typically, people either really like or really don't like proof by contradiction. So you might already be starting to form your opinion. I really like it, but I just like this whole class. So, okay. All right. So let's look at another one. I thought this was an interesting one because the way the book approached it using contradiction, I would never have approached it that way. So I'm going to show you the contradiction way, the book's way, and then my way, which would have used calculus. Okay. So I'm going to just write out the proof here. But remember, there's always a lot of scratch work behind the proof. Okay. There's always a lot of scratch work behind the proof. All right. So we are going to let x be in the closed interval pi over 2 to pi. Now, we want to get our contradiction. So we are going to assume for contradiction that sine x minus cosine x is less than 1. Because that's the opposite of what it's claiming, right? It's claiming it's greater than or equal to 1. So say, well, why can't it be? What if it were less than 1? All right. So here's the idea. If I'm looking at sine x minus cosine x, let's think about these pieces. So, whoops, don't do that, tablet. Go back. All right. So let's note that all right, so I want to note how sine of x compares to 0. I'm going to leave it because we'll talk about it in a second. And how cosine of x compares to 0 on that interval. If I'm from pi over 2 to pi, where am I on the unit circle? Yeah, I am over there, right? So sine and cosine, which one's positive, which one's negative? Yep, sine's positive because sine is your y value. Cosine's negative because cosine's your x, but your horizontal coordinate. All right, so sine is greater than or equal to 0. Cosine's less than or equal to 0. Okay. Well, if sine's positive and I'm going to subtract a negative, I'm definitely not going to get a negative overall, right? So sine x minus cosine x is greater than or equal to 0. Thus, so here we're going to get our string of equations. I know 0 is less than or equal to sine x minus cosine x, which is less than 1. If I have something between 0 and 1 and I square it, what can you tell me about its value? It's still between 0 and 1, right? It can't leave that. Okay, so let's square it. So 0 less than or equal to sine of x minus cosine of x squared is less than 1. All right, 0 is less than or equal to sine squared x plus cosine squared x minus 2 sine x cosine x is less than 1. But what is sine squared plus cosine squared? 1 minus 2 sine x cosine x is less than 1. All right. So I'm going to finish that sentence there because now I'm going to drop out the 0 part of the inequality. Okay. So I'm going to subtract 1 from the middle and the right side. And this is where we'll get our contradiction. But this means negative 2 sine x cosine x is less than 0. And that's coming from subtracting 1 from the middle inequality and the right of the inequality. Okay, so subtracting 1s. Why is that a contradiction? Sine's positive, cosine's negative, or 0, right? So if I take a negative 2 times a positive times a negative, it's going to be positive, or 0 if I have a 0 in there, right? So, which is impossible. Since sine of x greater than or equal to 0 and cosine of x is less than or equal to 0. Thus, sine of x minus cosine of x is greater than or equal to 1. Because if it were to be less than 1, I'd get a contradiction. Questions on that one? Okay, so the reason I dropped off the 0, this inequality, when you write inequalities like that, it's basically two statements, right? I'm saying 0 is less than or equal to this mess, and also this mess is less than 1. What I determined, well, what the book determined is at this point, I don't need that first statement. So I just ignored it and focused on the statement I needed, which was that the mess was less than 1. We only needed the 0 really to get from that step to that step. That said, okay, when I square it, I'll stay between 0 and 1. That's the only reason we needed the 0. So once we didn't need it, we could actually drop it and get rid of it. Yep. Other questions on that one? Say that what weren't equivalent. Mm-hmm. Well, but if you subtract the 1 from the other one, you would have had a -1 less than or equal to stuff less than 0. So yeah, you'd have to subtract it from both. Yep. Okay. Well, let's look at the calculus way of doing this. Okay, that would be a direct proof. And so here's the thing, that contradiction was super clever, but who knows how much messing around with the equations and the algebra it took before they hit on this idea here, right? This is not the first thing you'd go of, oh yeah, I'm just going to square it and see what happens, right? So let's look at a direct proof. Okay. All right. So here's the idea. I'm going to use ideas from Calculus 1. I'm going to take my function. So maybe I should write a little scratch work off to the side so we're all on the same page. So I'm going to let my function be sine minus cosine. And I'm going to look at that on the interval from pi over 2 to pi. See what it does. Well, let's take the derivative of that function. Derivative of sine is cosine. Derivative of cosine is negative sine. So I'll get cosine plus sine. Okay. Now I'm going to do the first derivative test. So this, I happen to know, this equals 0 at 3 pi over 4. Okay. It equals 0 lots of places, but that's the only one in our interval that's going to give me 0 there. Where sine and cosine match, except they're off by a negative. Okay. So let's make our little chart. So my x and my derivative. Let's put our endpoints in here. So at 3 pi over 4, my derivative is 0. At pi over 2, if you plug pi over 2 into the derivative, you get a positive 1. So my derivative is positive. Okay, at pi, if you plug pi into the derivative, you get a negative 1. So the derivative is negative. What does the first derivative test tell me that means about that interval? What's going on? Yeah, it increases up to whatever value 3 pi over 4 gives it and decreases away, right? So 3 pi over 4 is the maximum value, okay? All right, and pi over 2 then is going to be my least value because that's my lowest point I'm allowed to plug in, right? And pi it's also going to be a lowest value because that's the last point I'm allowed to plug in. So let's see what we get. So my original function at pi over 2 equals 1. My original function at pi equals 1. And what happens between pi over 2 and pi? It increases up to a bigger value and then decreases back down to 1. Let me go back up to the statement. What are we trying to prove? That sine minus cosine is greater than or equal to 1. And that's what the calculus shows, that my smallest value at those endpoints is 1, and between them it increases away from 1 and back down to 1. Okay, so so you would write all that logic in words, right? So let me do what I'll sometimes do in classes when I'm running a little low on time. I'll do what I call a proof outline. This is not what you turn in for homework. This is just us showing the logical steps in the proof, okay? So we're going to consider f of x equal to sine of x minus cosine x on, here we have closed interval, pi over 2 to pi. All right. Then f of x has a, here we go, local or relative, I don't know what word you guys used in Cal 1, but local or relative max at x equals 3 pi over 4 since f prime of pi over 2 is positive or greater than 0, and f prime of pi is less than 0, f of x increases away from f of pi over 2 and then decreases down to f of pi. I'll even put in parentheses, i.e. f of pi over 2 and f of pi are minima on this interval. Right? Since f of pi over 2 equals 1 equals f of pi, this is the smallest value f of x takes on this interval, something like that. So this was almost a full proof. It was just a little sloppy. So the smallest value f of x takes on this interval. And that's our logic. So that's not as nicely written as a regular proof, not as nice and clean, but that's all the logic there. All right. Any questions on that one? So, and we're going to go on to the next page because it's not a long page, but when you're turning in your homework, when you're doing homework, if it does not specify the method for you to use, you can use any appropriate method. If it says, though, in the directions, which some of them do for this specific homework, use contradiction, you have to use contradiction, okay? Because it's wanting you to practice using that method. But after this section, it'll very rarely tell you which one to use. So, all right. Cool. So let's look at the last page. It's just got 2 things on it. Another book problem. So if I have an integer, 4 will never divide n squared plus 2. That's what it says. 4 will never divide n squared plus 2. So for contradiction, what am I going to assume? Yeah, there does exist an integer such that what? 4 does divide n squared plus 2. All right, so n squared plus 2 equals 4k. All right, so there are 2 different approaches I could take here. One approach, I could then consider cases. I could say, well, let's take the case where n is even and let's take the case where n is odd. You'll get a contradiction in both. I can actually rule one of those cases out right away looking at this though. Why can't n be odd? You're right. Yep, I need an even plus 2 to equal an even, right? So you can rule out right away that n is odd. Now, if you did a case for n being odd, that's fine, you'll get a contradiction. But we can rule that out and say n is even. All right, so n is going to be 2l. Let's see what that gives us. 4l squared plus 2 equals 4k. What do you want to do? Okay, square root would be too much, but there is something we can do algebra-wise kind of like that. Divide by 4, there you go. Because then we get l squared plus a half equals k. Or if we want to be super explicit, a half is k minus l squared. What do you think?
No.
Heck no, a half is not an integer, but k minus l squared is an integer. And so that's our contradiction. You'll notice we get a half being an integer a lot as a contradiction at this level, right? That's because we deal with even odd, so we divide by 2 or 4 or whatever a lot. So, okay. So that one, I'll leave space for you to go back if you want to try to write out the full proof. Now, this is a book problem, so the answer's in the back, right? It's an odd book problem, but that's the logic, okay, that I would use. But I want to have time to look at this last one, because this last one, I'm not going to tell you a method. I want you to think and decide what you would do. So every integer squared is congruent to either 0 or 1 modulo 4. So take a second and think about how you would want to approach that. All right, what are people's thoughts? Well, so you're saying take this integer and do cases, like even, and then see what happens when you square it, and then odd.
Because it's in 4, so if you figure out if it's one or the other for each case, even if odd, you know that for every integer.
Yeah, no, absolutely. And that is the best way to approach this. That's a direct way, right? So you say if I have an even integer, right? So it's 2k. What happens when I square it? 4k squared. Is that 0 or 1 mod 4? Yep, that's 0 mod 4. What if it's odd? We have 2k plus 1. What happens when I square it? Plus 1. Is that 0 or 1 mod 4? Yep, that's 1 mod 4. Okay, so yeah, that is best way to approach this. Most straightforward way. If you tried contrapositive or contradiction, you're having to negate that 0 or 1 mod 4. Now, if you've done a lot of work with modulo, you know that the opposite of being 0 or 1 mod 4 means it has to be 2 or 3 mod 4, and that would give you something to work with, but it's still messier. Okay. So yeah, your proof then would follow those lines. You would have case 1 and case 2, right? So let me just kind of set up the proof since we got time. So proof, let n be an integer. Case 1, n is even. Then there exists k in the integers, blah, 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 right? Till we get to n squared equals 4k squared. So 4 divides n squared minus 0. Thus, n squared is congruent to 0 mod 4. So the stuff I skipped in the dots, that's our normal, right? Oh, it's even, so then n equals 2k, so n squared is 4k squared. Okay. Case 2, n is odd. Then there exists k in the integers, da, 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 da. Why am I allowed to use the same variable k? Because I completely finished with the first one, right? So it's gone, it's done, I can reuse it. Absolutely, you could use a different integer and it'd be perfectly fine. N squared equals 4k squared plus 4k plus 1. Oops. So I'm going to write an extra step here. N squared minus 1 equals 4k squared plus 4k. Thus, 4 divides n squared minus 1, meaning n squared is congruent to 1 mod 4. And then our conclusion, we'd say, in either case, n squared is congruent to 0 mod 4, or n squared is congruent to 1 mod 4. Now this one happens to be an exclusive OR in that it'll never be both at once, right? But sometimes an OR, you could have it be both at once, just not in this particular one.
You showed that n squared is zero. What about just n?
Okay, yeah, so what does the problem say? It says every integer squared is
Oh,
congruent.
yeah.
So yeah, it wouldn't be true if it was talking about just n, because n could be 2 mod 4, 3 mod 4. Those are valid. Like 6 is 2 mod 4. Yep. Any questions on contradiction?